on our plenary session, it's a great pleasure to invite Dr. Daniel Renner. His presentation will be high-power watt-class diode lasers, overview of recent progress. And I know his bio, but I need to read here. He grew up in the southern part of Chile. He received his Bachelor's of Engineering degree from the University of Chile, and then in his early 20s, he went to the University of Cambridge in England for a PhD in optoelectronics. At the time, it was a new field of studies at the time, right? Now, decades later, he has lived through the whole range of experiences that related to the research, development, manufacturing, and commercialization of complex photonic devices and systems used in communication, sensors, and industrial applications. In the past 34 years, Daniel has been directly involved with the growth of 4 photonic startups in the United States: Ortel Corporation, Agility Communications, Aeros Photonics, and Freedom Photonics. This gives him a unique perspective on the working of high-tech, the small business, and the process of transforming leading-edge photonic technology into products. This is amazing. And Daniel is currently at Atacama Optics and Electronics, Santa Barbara, California, where he provides support to photonic companies in business development aspects. Additionally, Daniel is chair of the IEEE Photonic Society Industry Engagement Committee. Please, Daniel. Can you use both of them? Okay, that's fine. We'll keep this one. Where's the time here?
Where is the...
Yes.
Good morning, and thank you, Newton, for that wonderful introduction. My name is Daniel Renner, and this morning we're going to talk about high-power diode lasers. High power meaning single diode lasers that can generate about a watt or more. In order to do this, I'm going to very briefly, one slide, talk about a little bit more about my background, just so that you understand where my points of view are coming from. And then we are going to get into the topic, showing some numbers for the state of the art for high-power diode lasers. And then talk a little bit about the motivation. Why do we need these high powers? What's the big deal about having these devices that can generate a watt or more? And some of the companies that are active in this area, so that you have some flavor for it. I'm sure that some of you here might be involved in things that are related to this, and this will be something that you know. But for others, so that you get a little taste and maybe get excited about this topic and get into it a little bit deeper. And then we'll talk about some practical examples for high-power diode lasers. There are many different architectures and many companies. I've chosen, I've chosen 6 companies that I'll highlight a little bit more. I think they're interesting about what they're doing. So that's the plan. So here a little bit about my professional trajectory. As Newton mentioned, I'm originally from Chile, actually from the south of Chile, from Patagonia. So I'm from this part of the world, and so that you understand, I come from a similar perspective as what the majority of you do. And from there, I went to Cambridge in England, where I did a PhD, and then I worked for 2 large companies, ITT and Rockwell. After that, I discovered startups, and I worked in 4 startups sequentially over a period of about 34 years. The last one being Freedom Photonics. Is there a pointer here? No. Anyway. And there we worked on high-power lasers. So I'm going to talk a little bit specifically about what we did at Freedom Photonics on this topic. And as Newton mentioned now, I'm with Atacama Optics and Electronics, which is a consulting company, and I help companies grow, hopefully. Not always successful, but that's what I try to do all over the world. Thanks very much. There. So let's go into state-of-the-art performance, and then nothing happened. Oh, there. So for single emitter devices, these are just single diodes. The current state-of-the-art nowadays is of the order of some tenths of watt. So you can generate 10, 20, 30, 40 watt, something of that nature. That's kind of the highest achieved at this point. And as you can see, we've evolved from the very beginnings, where the output power was in the microwatts to, say, 10 milliwatts and so on, and further going up here. For the past 20 years, the peak output power has increased by a factor of 2 per decade, but you can see that the progress has slowed down. Can we continue making the output power of diode lasers grow by a factor of 2 every 10 years? Forecasting is a difficult topic, and I am reluctant to get into this, but my hunch is that we're saturating. I think it's unlikely that we will double again, that we will get 80 watt out of a single diode in another 10 years. We're closing, I think, again, it's never say never, but I think we're because of physical limitations, we're fighting nature now very hard. I think that's some 50 watt or so is what we can expect out of a diode laser. Now, different wavelength ranges are not the same. As you can see, the highest powers are obtained at wavelengths around 900 nanometer to a micron, somewhere there. Immediately below that, around 700, 800 is also pretty good. There's not much of a distinction. But this is really, if you want high power, this is the preferred range, the near infrared, from just outside red all the way to about a micron. And there are 2 areas that are really bad, and you can still get a watt or more, but it's not as easy as in this range, around sort of 600 and something, which is the red, and then way in the infrared at around 1550. It's very difficult to get high power. You can still get a watt, though, as shown here. And then when we get down in the blue, again, it becomes somewhat easier. You can get 6, 7, 8 watt or so. Not as much as here, but better than in the difficult windows. So it depends on what you want. If you want high power, you don't care what wavelength, you should be here. If you need to operate at these wavelength ranges, well, you have to have those wavelengths, but you can still get decently high power. Now, the way to get even higher power is by forming arrays, of course, and this shows the state of the art for arrays over time. And these days, you can get something of the order of 100 kilowatt out of an array. This is a huge amount of power. And as you can see, similar to the graph before, now since the 1990s, we've actually been increasing by an order of magnitude per decade, factor of 10 every decade. And my forecast here is quite different. In terms of arrays, the sky is the limit. It's really the number of elements that you can configure in an array is limited by technology of being able to make that array, and mainly due to limited by heat extraction. The arrays, if you're generating 100 kilowatt of optical output power, even the best diode lasers have efficiencies of 70%, say 2/3. So for 100 kilowatt, you're still generating 50 kilowatts of heat. So you need to extract 50 kilowatts of heat out of a tiny area. The ability to do that is really mainly what limits the size of the array. And my prediction here is that there is a lot of scope for improvement there, and that we will continue progressing at an order of magnitude per decade. And by 2030 or thereabouts, we will be able to have a megawatt array. So why do we want these powers? Why do we need 10 watt out of a single diode? Why do we need hundreds of kilowatts out of an array? And there are many reasons. There are many applications for this kind of device. The main one actually being for industry, in manufacturing. And that is something that is kind of very applicable these days in metal cutting, like showing in this picture. These days, not necessarily direct diode lasers are used. You can use solid state, typically solid state laser, or fiber lasers are used. But with diode lasers increasing in output power, the ability to use direct diode lasers for its applications become increasingly possible. And obviously there are cost advantages in using directly a diode compared to a more complex laser. So manufacturing is a key application. Also pumping other laser systems for other applications, like shown here. Sensing is a really important application. The diagram here shows automotive LiDAR. The automotive field, self-driving cars seemed to be the big hope back about 10 years ago. Actually, at that time, I saw predictions, and predictions, as I said, are always difficult, that self-driving cars would start to be pervasive. You would find them anywhere in 2023. Well, 2023 obviously went by. You can see self-driving cars. Yesterday, at the talk, it was mentioned that if you go to San Francisco, you see several basically taxis going around. Now you can see them in many other cities in the United States. But the application is limited. It's limited to that. The numbers of cars are not very large. And so automotive LiDAR still continues being the big hope of the future. Again, predicting, my expectation is that this will become a feature in the future. Who knows when there will be self-driving cars that we can all buy. But this didn't happen in 2023. I don't think it's likely to happen in the foreseeable future. But within the next decade, it's quite possible. So this is a future, very important application for high-power lasers. This kind of LiDAR relies, for automotive, it has to be very inexpensive. So a high-powered diode laser is key for implementing this, and it's in the process of happening. Defense is obviously a very important application. Then medical, biomedical, as was described in the earlier talk very brilliantly. There are a lot of applications, laser surgery, for example, as shown in this picture. Agriculture as an area where Deborah has been working, and many other people here. There's a whole team working in agrophotonics. High-power lasers for a number of applications, like the picture shown here for a robot which basically is killing weeds by shooting them with a high-power laser are important applications. In communications, here, for example, underwater communications, it's becoming an important area. For displays and lighting, big displays that you can see in Times Square or Piccadilly Circus, those displays use red, green, and blue high-power lasers in some cases. Then for research, spectroscopy, and so on and so forth. So the number of applications is large, but it's a very fractured market. None of these applications, as I was saying, automotive LiDAR was expected to dominate. Well, it didn't, or at least it doesn't right now. It won't for a while. The market is fractured, and every one of these applications requires a different wavelength, different output power, different spectral characteristics, and it's very difficult for a manufacturer like I have been to address all of this. You have to select where are the key applications. It's a market that is highly fractured and not that large. The high-power laser diode market is estimated to be about $550, $600 million now. Now that sounds like a big number, $600 million. But in this game, as I'm sure you're familiar, and for a market that is fractured, as I mentioned earlier, it's okay. I have played there and I've lived thanks to that, but it's not a very, for reference, the electronic IC market, for example, will be about $1 trillion by the end of the decade. It's about $800 billion right now. So it's many orders of magnitude larger than this. So why are people interested in a market that is very fractured, that, I mean, it's large, but not that large? Well, the reason is that it enables markets that are much larger. As mentioned earlier, a lot of these robots and communication systems and medical equipment and so on and so forth could not exist if this don't exist. And so the market for the applications is much larger. Actually, this is difficult to estimate. It's estimated that the market for photonic systems is of the order of $400–500 billion. So not all of that, but a good chunk of that is enabled by this. So it's the enabling aspect that justifies it commercially. So what companies are active? And I have two sheets, actually, this and that one. I have a total of 22 companies, and that's not all. I just mentioned the 22 that I think are dominant and came to my mind. But there is something of the order of many tens, some number close to 100 companies all over the world working on in this area. And some of these names you recognize. Oops, sorry. Coherent is a large photonic company, as we know. Lumentum, Trump laser is very important in the area of lasers for manufacturing, and so on. The company that I mentioned that where I worked is Freedom Photonics. We sold it 3 years ago to a company that works on automotive LiDAR, Luminar technologies, so it's now Luminar Semiconductors. And obviously this company I know well. I was there and what we developed, so I'll get into some detail of what we did at Luminar later on. And now in a consulting capacity, I'm working very close with Kyocera SLD, which is a company also based in Santa Barbara, where I live. So from a point of view of how people are making high-power diode lasers, I'll focus on these two. And here there are some more. Actually, you can see Kyocera SLD here as participating in the display and lighting areas, but they're also working in underwater communications. You can see Trump, which is probably, as here, Trump, Genoptic, and IPG are very strong on materials processing, and so on and so forth. So some practical examples. I'll start with Kyocera. As I mentioned, I'm consulting with this company. Kyocera was, the SLD was founded in 2013. It was a startup in the Santa Barbara area. In Santa Barbara, we're lucky to have a very efficient photonics ecosystem. There are constantly companies created. So the company was founded to exploit developments that happened at the University of California in Santa Barbara in gallium nitride. So it was founded with the intent to make lasers based on gallium nitride on the blue, violet, green wavelengths, and so on and so forth. And it was bought in 2021 by Kyocera, which is a Japanese company, but it operates as an independent company, Kyocera SLD. And the main technology, as mentioned, is gallium nitride. In fact, it's the only commercial United States-based gallium nitride laser company. The novel aspect of their technology, the unique aspect, is that they have a unique patented transfer process that helps the manufacturability and thus reduces cost. Gallium nitride wafers are not very large. They're relatively small, of the order of 2 to 3 inch diameter, very, very small. So that's how you need to start. All the epitaxial growth is done on gallium nitride substrates. So you grow a wafer which has very densely packed devices in it. And then this is where the trick happens. There is a transfer process that then assembles the diode lasers grown in gallium nitride onto a silicon, a 4-inch silicon carbide carrier. So a wafer that is twice the diameter. But the transfer is not just one by one. It's done in a way that the devices are spread out. So the density lowers. What are the advantages of this? You now have a 4-inch carrier with which you can then use automated equipment and equipment that is sort of silicon type if you want. And also you can then subsequent processes which include passivation, facet etching. The facets of the lasers are etched once it's transferred to silicon carbide, and all of this is done then now very efficiently in the larger wafers. And then they end up with fully processed lasers on silicon carbide. So it becomes a very practical way of dealing with wafers that initially, just because of the state of gallium nitride crystal growth, are very small. And the results show. So here, for example, is a blue laser, wavelength of the order of 445 nanometer, a single laser, generating at room temperature 8 watt. This is actually a record for a commercially available device. The state of the art was about 5-6 watt until recently, but now it's grown to this level at this particular wavelength. Violet lasers are also made at, say, wavelengths of just above 400 nanometers, and similarly of the order of 8 watt has been manufactured at these wavelengths. With fairly high wall plug efficiencies, efficiencies somewhere in the 40 to 45% are typical. Now, as I mentioned, at wavelengths around a micron, efficiencies are two-thirds, 60-70%. So there's still some distance from here, but there are intrinsic mechanisms in the diode itself that limit the efficiency, and those are the ones that need to be fought, so that then, say, at blue wavelengths, one can get output powers like the ones I showed you that are possible at a micron. But 8 watt is pretty good for blue and violet. The devices are reliable, that has to be shown. So here there are some devices that have been subjected at high test conditions for 4,000 hours. And there are some variants also that have been developed out of this. There are some companies that require, some applications that require even higher power. They don't care too much about the spatial configuration of how the output power is coming from or like. So this is really a small array, an integrated in a single chip, an array of 2 lasers, and in this case, this is generating 11 watt. Then some higher level of complexity chips have been made as well, like distributed feedback lasers. This is a DFB laser. One typically finds that in DFBs, for various reasons, the output power is about an order of magnitude less than what you can get out of a Ridge Fabry-Perot laser. And that's kind of approximately the case here as well. Output power of 400 milliwatt for a blue diode. As you can see, the wavelength is in the 400 and something. And so this is actually, we're not aware of anybody else making blue DFBs. So, and for any DFB, 400 milliwatts is fairly high power. So this is one more complex type of device. The other one is a MOPA type structure that is in development right now. This is a now pretty standard integrated structure where you have a master oscillator and power amplifier integrated on a single chip that we pioneered at Freedom 10 years ago, but now it's being adopted more or less globally, and Kyocera is working on this on the Blue as well. Then one interesting sub-product, consequence, if you want, of the Blue lasers is they have developed a source of white light, which is basically a phosphor pumped by a blue laser. And this has tremendous applications in illumination and sensing, power transfer, secure communications, and so on. And in fact, there is a particular device where you can choose between white and infrared illumination, or both, at the same time. This type of device is used for indoor Li-Fi, for example, that is like Wi-Fi, but using light instead of radio waves. And there you can illuminate in white, say, and communicate in infrared, as an example of the devices that use both wavelengths. For underwater communication, this is transmission in water. And as you can see, there is a really nice window in the blue. And so blue lasers are quite ideal for communicating underwater. Let's talk just in one slide. This is not high power lasers, it's photodiodes, but you need photodiodes to detect the blue lasers, and Kyocera also makes very high speed and high power devices that are capable of handling high power, and as shown in this diagram, among the best in the world. So let's move now to what Luminar Semiconductor, prior Freedom, where I was, has done. Luminar actually acquired Freedom Photonics, but also has acquired other photonic companies. For example, Optogration, that makes high dynamic range avalanche photodiodes. So now they have 4 facilities across the United States. And basically the line includes from packet chips and modules to some simple optoelectronic systems for applications in defense, sensing, automotive LiDAR, which, as mentioned, is the reason why Luminar bought Freedom Photonics, and optical communications. So this is actually a chip. This is actually how a tapered master oscillator power amplifier looks like. You can see the master oscillator portion that is here, which is sort of a straight device, and then how it gradually expands the sort of the trumpet the tapered section that is the power amplifier. It's a very long device, and this has been a workhorse to go over a watt at the wavelengths that are difficult, like at 1550. So in principle, it's not a single diode laser. I mean, the diode laser is here, but it is a single chip that incorporates both a laser and a power amplifier. So in that sense, even though it's only 2 elements, by having 2 elements, it's already a photonic integrated circuit. Then one interesting area of application is for using then, and this is the main application, as I said, why Luminar bought Freedom, is to apply this for LiDAR. LiDAR systems, in a LiDAR, the higher the power, the more range you have, the further you can see. So nowadays, fiber lasers and other type of high power lasers are being used, and the thought then is to basically replace that by a single chip that consists of the laser and the power amplifier. So in gallium arsenide material system, which is a shorter wavelengths, output powers of the order of 10 watt have been demonstrated, and in the indium phosphide material system, at the longer wavelengths at 1500 and even 1600, output powers of 3, 4, 5 watt have been demonstrated. Again, this is because of having the power amplifier. That is basically what enabled us, as I say, now almost 10 years ago, maybe 8 years ago, to break through the 1 watt barrier. Freedom makes the integrated MOPA, but also just a tapered amplifier that then people incorporate with other elements, and that works pretty well as well. The amplifiers have very fast response. For example, here you can see extinction, 20 dB extinction in about 100 nanoseconds by switching off the amplifier, even faster to turn on. The line width is preserved through the amplifier. Here you can see the line width of the seed and the line width then through the amplifier. The shoulders are raised a little bit, but certainly the shape and the width at 3 dB or even at 10 dB is preserved. This shows a tunable configuration where you're getting high power with a so this is the power amplifier being seeded by a tunable laser. The seed is in blue. The output following the amplifier is in red. You can see that the sort of non-lasing wavelengths are amplified by the amplifier, but it's hard to distinguish. There is a red line. The amplified blue line comes through the amplifier and it still dominates. This has many other applications other than automotive LiDAR. For example, LiDAR for atmospheric methane detection. This is a program where we were funded, again, 5-6 years ago by NASA. And NASA has deployed this. It's very important to detect methane in the atmosphere because actually it is the most important global warming gas. It has tremendous heat capture ability, unfortunately, and massive amounts of methane are being released into the atmosphere constantly. So it's very important to measure the amount of methane in the atmosphere, and this is being done from satellites and from airplanes right now using our lasers. Also data communications using high power lasers, both amplitude and phase modulation, and some reliability data as well. This showing almost 14,000 hours with no change whatsoever. Here there is a superposition of the light output and current of devices from before and after. So now very quickly, I emphasized Kyocera and Luminar. Now just very quickly through a few other companies. This is a company in Finland called Modulite, again showing that they're doing this configuration of MOPA, but in this case a DBR is the source, so they get a very nice line, in this case at 780 nanometers, and still getting very high power because of the power amplifier. This is from Coherent, the very large company, high brightness lasers for LiDAR applications. These are arrays. They have compared arrays of VCSELs and arrays of edge-emitting lasers for LiDAR applications, and in this case they're getting massively high power because in this case I think it's something like 22 or 28 lasers or something like that. Now from Trump, this is another way of making an array. This is a normal way of making an array. These are stacks. In this case are 52 bars generating tens of kilowatt. And here there are 32 bars. This is generating 20 kilowatts. This is generating 50 kilowatts. So unfortunately there is no sense of size here, but these arrays are really small. They're smaller than your iPhone. And so again, if you're generating, say, 50 kilowatt of optical output power out of this, you're generating 25 kilowatt of heat. that needs to be actively extracted. And finally, a collaboration, this is between Ferdinand Brown and Lawrence Livermore, where they are developing high-power diode lasers pumps for fusion applications. So this uses a massive, large amount of diode lasers to get fusion going. So that's the story. And to conclude, it's really amazing. When I started and we were dealing with 10 milliwatts laser, I never imagined that you could get 10 watt out of single diode laser, but it's happening. Arrays with 100 kilowatt and more, as I've said, are possible. The market will be about $1 billion by the end of the decade, but it's very fractured, and really the justification for all of this is in the applications, not in the high-power diode lasers themselves. MOPAs are an important way of making them happen right now, and progress will continue as predicted, as I said. Thank you very much.
Thanks, Daniel. Question? You have a question?
Okay. Good morning, Daniel. I think that when you're talking about high-power laser, you're talking about a continuous wave laser. There are some challenges for get high power in maybe femtosecond laser and these, new ultra-fast photonics. But the question is, there are some challenges for get high power in femtosecond lasers.
In what kind of laser?
Femtosecond.
Oh, femtosecond. Yeah, I mainly talked about CW or QCW, quasi-CW lasers. Femtosecond lasers are really a totally different beast. It's a different kind of architecture. You can get significantly higher outputs because obviously you're dealing with very short pulses. And so heating is always an issue, but the shorter the pulse, the lower the problem. So as I mentioned, in this kind of device, you're fighting heating. In the case of femtosecond devices, you're fighting the sort of intrinsic materials and the configuration of the laser that is being designed to obtain the very short pulses. And it's a different sort of problems that you have there.
Any other question? One more here.
Very interesting talk. I had never heard that you could produce so much power out of a single diode. I'm wondering what kind of optics is used after the laser, because with 10 kilowatts or 50 kilowatts of light coming out, even a very small residual absorption in a lens would probably destroy it in the long run. How is that controlled? What kind of materials are used for the optics?
That's a very good question. And yet, well, first, every time I say or I read that you can get 10 watt out of a single diode laser, I'm still amazed. And as I say, I started with 10 milliwatts, and I never imagined we would get it to 10 watt. And even though it's a reality, somehow it blows my mind. But it is a reality. And yes, how do you extract beyond the facet of the laser 10 watt or 50 kilowatt? I mentioned heating being one limitation. That's another limitation. And the issue is, one of the problems, diode lasers are fantastic. They're small, they're tiny, they're efficient. They can generate high power, but their output beam is terrible. Basically, it diffracts, particularly in one direction, very widely. So all of these diodes are built in exactly the same way, and the far field pattern is very asymmetric and astigmatic. And it's very wide in the plane normal to the laser, and it's narrower in the plane of the laser. typically it could be 40 degrees wide in one direction and 5 degrees or less in the other. So in order to get the power out of one device, mainly cylindrical lenses are used to first change the shape of the beam to a more circular one. So you correct the widely diverging lens so that it becomes more parallel. And then you can use a spherical lens to narrow the beam even further. These are glass, specialty glass lenses. They're not very thick, so they're not really very absorptive. They don't really, say 10 watt coming out, it's imperceptible, the absorption in the glass going through two lenses. So the first lens typically is called a fast axis correction, FAC lens, and then the collimating lens. So that is a typical structure in one lens. Now, the typical structure, and here is the problem, and this is where some progress needs to be made. In an array generating, say, 50 kilowatt, where there are thousands of lasers, is essentially the same. You correct now thousands of lasers. You need, normally in this case, what happens is lasers are all formed into bars, so you assemble bars having 25 lasers, say, for example. So in one dimension, the array, say, could be 25 lasers in a bar, and then you stack these bars one on top of the other. So the first lens, the FAC lens, is now a cylinder. You place it all the way across the bar, even though you need it only where the lasers are, but it's just cheaper to have a cylinder, half a cylinder, placed in front of the bar, followed then again by correcting lenses to collimate the beam. So these arrays, these stacks, from a mechanical perspective, from a thermal perspective, from an electrical perspective, from a lensing perspective, are a mess. It's very complicated and makes it very expensive. I hope that answers your question.
Okay, I think we'll have time to we don't have time for more discussion, but I'm sure you'll have some more questions. You can ask Daniel during the coffee break or later in the conference. So let's thank again Dr. Daniel Renner.